Okay, we'll continue with noise and mixers. So why did we leave off last class? So we looked at the flicker noise, right? We did a general analysis, looked at the flicker noise from the switched pair. We looked at the noise from the resistor, the load, then we looked at the noise from the transconductor, then we started looking at the noise from the switch. For the noise from the switch, we looked at the flicker noise first. We found that flicker noise typically goes either it goes away from the frequency of interest, right? We saw that it goes around 2LO and 4LO and so on, right? And we saw that for receivers it's not a problem, for transmitters it could be a problem. Okay? Okay, so let's look at switch thermal noise. Okay, so we'll do the same thing as we did last class. So let's say the noise has some weird profile like this. Okay, this time, and what we saw last time was, if you look at the output noise, okay, we could represent it as a series of pulses, right? And the pulse width delta t depends on the noise voltage and the slope at the zero crossings. Okay, and the amplitude of the pulse was 2it. Okay, where it is the tail current. Okay, and the other thing is it occurs every half period. Okay, so what we'll do is, to simplify the analysis, we'll replace it with another train of pulses, except that instead of having the width, the pulse width change every period, we'll keep the pulse constant, the pulse width constant, but change the pulse amplitude such that the overall noise added is the same. Okay. Okay, and so on. So what we are going to do is, the pulse width is a constant Ts, and the height is 2it over s times Ts. And remember that the slope s s times Ts will decide the noise. Okay, and actually this is constant, but that times Vn. We are going to allow this pulse train to sample your Vn, okay, to give you ION. Okay, so let's look at this guy. So what is Ts? So let's say you're going to plot the differential current versus input differential voltage. Okay, so the switching time period, right? The switching voltage is delta V. Okay, and the time it takes to switch to the current is Ts. Okay. Okay, let's plot. This is your GM as a function of voltage, and this is again delta V. Okay, what is this GM of V? If you have a delta V, it's 2it over delta V. That is your GM of V. So plot versus time, GM of T. The effective GM of T of the differential pair is going to look like this. Okay, at the switching instant you're going to have a large GM, after that it will be 0, right, because the current is completely switched. And what is this? This is Ts. Okay. What is Ts? It's nothing but delta V over S. Okay. For all this, you're going to assume that delta V is much smaller than VLO and so on, right? It's a very small delta T. Similarly, delta T is much smaller than TLO. All those approximations. Okay. So don't worry if you don't understand a lot of this, because I'm skipping a bunch of steps. Okay. So just take it as it is for now. What we are more interested in is the final answer. And GM is, okay, and we know delta V in terms of Ts, so it's okay. Two IT over STS, that's your GM times Vn is your output current. Okay. What else do we know? We know Vn squared. Okay, it's 4 kT over 4 kT gamma over Gm. Okay. So now we are going to make a small leap. Okay, leap of faith. Let's say for now. So we are going to say, I'm just going to give you the result. Okay. So this is the beginning of the analysis. There is some autocorrelation integration you have to do to get the final answer, but I'll just give you what the final answer looks like. You can show that this guy is 2 by T LO okay. This you can show. So you do 2 by T LO integral 0 to T LO by 2 of some function, okay, and you get something like this. Similar to what we did last class. We did this, right, to find the average of the function, to find the average of the noise current. We did this. Remember that, right? So it's similar to that. We do this. So, okay. And we're just going to rewrite it like this, slightly differently. So of course all of these have delta F, right? Yeah, of course. Yes. Okay, what is this? We already know these two cancel. Gm is nothing but 2IT over STS. Four kT gamma times sorry. Okay, that's S times TLO. So first of all, what does this tell us? The noise voltage is inversely proportional to S, which is the slope at the zero crossing. So if you want very low noise from the switches, you want your zero crossings to be as sharp as possible. I mean, that already you knew that, right? Because during the zero crossing is when the switches actually contribute noise. So it makes sense that you want them to be as narrow as possible. Okay, so that it does tell you. Okay, and remember from last class that you did want S to be large as far as linearity was concerned, because you had that CGS mismatch between the two differential paths. Okay, so that is definitely one colliding factor between noise and linearity. S should, oh sorry, did I write this? Okay. S should be large, right? For linearity we saw that S should be small. Okay, because the displacement current depended on d VLO minus dVx, d of VLO minus Vx over dt. Remember that, right? So what else do we know for a sinusoid? If you have sinusoidal input, you can find the slope at the zero crossings, and it turns out to be IT over pi VLO. Okay. What is the other thing you notice about this expression for the switch noise? The other interesting thing is, normally if you look at the transistor noise, let's say circuit noise, it depends on the, let's say, the GM of the transistor. So it depends on the bias current, it depends on the width, right? Here you see that it depends on the bias current, but it's totally independent of the width, right? So if you size the, it does not depend on how you size the switch. The reason for this is because, so if you, let's say you have a certain size, you double the size of the switch, okay, what happens is the noise goes up, okay. So the input, what happens is the current noise goes up, but the input referred noise actually goes down as you make the switches larger, okay. But what happens is, remember what happens to the pulse width? The pulse width becomes smaller and smaller, okay. As you increase the width, the transistor switch faster naturally, okay. So as the pulse width becomes smaller, what happens to this? So if you look at the output noise profile, right? So let us say the output noise looks like this. So this is your output noise floor, okay. So let me also draw your we know that noise goes from 2FLO and 4FLO and so on, right? That's the rate of the switching, okay. That's your so you have FIF here, okay. So you have noise from here, okay. So you have noise from here and so on, okay. But obviously at a certain point you have to stop. What is that point? So if you look at the pulse train which is sampling your noise, okay, with this TS, what does it look like in the frequency domain? Looks like a sinc function, right? That's at 1 over TS. So what happens when you increase the width? So obviously there is only a limited amount of noise. It's not unlimited amount of noise which adds in, okay. So what happens when you increase the size of the transistor? TS drops, which means 1 over TS, the sampling bandwidth increases. So you actually add in more noise, but the input referred noise floor actually goes down. VN actually goes down. So overall it ends up compensating, so that your switch noise, the output noise due to the switches is independent of the switch width, okay. So is IT over pi LO. So you can add all the three, right? You can add the load noise, you can add the switch noise, you can add the noise. So the total noise happens to be, you can rewrite it like this. That's your load noise. Okay, this is your total output noise, the voltage noise. Okay, you have the contribution from the resistor, from the transconductor, and from the switches. Is that clear to everyone? Okay. Let's look at the other source, which is indirect switch noise. Actually, before that, if you actually look at this guy, GM of the transistor, this is the GM of the transconductor stage. Okay, you can write that in terms of you can write it as IT over twice the overdrive, VGS minus VT of the transconductor. Okay. So if you want to make it more linear, you know that you want to increase V overdrive. Okay. Right. So it becomes more linear. But then eventually what will happen is, so the noise of this guy goes down. Eventually it becomes comparable to this guy. And when does that happen? That will happen approximately when VLO becomes comparable to your V overdrive. Okay, if you are driving with, let's say, a couple of hundred millivolts of swing, or probably more, if your overdrive becomes that high, then the two noises become comparable. Okay. Okay, let's look at the switching pair again. Assuming that there is some parasitic capacitance Cp at the common source node. Okay. What we are going to do is, okay, you can show that this, you can redraw the circuit slightly differently for the two half cycles. Okay. So first of all, actually before we do that, let me add the, okay. Sorry. Or just Vn. So during the first half cycle, so you only have this guy. You have IT, Vn and VLO here. Okay. During the second half cycle, you have the other side. You already replaced the input referred noise of both devices as Vn. So okay, this is the first half cycle, this is the second half cycle, and the two things are totally independent. Okay, then what we are going to do, we are going to redraw these two again slightly differently. Okay, and so it goes between 0 and Vn, between the two half cycles, and once you do this, the two things are equivalent. Is that clear? So what is the difference between these two? The difference between these two is just Vn. Apart from that, the input voltage is the amplitude VLO, the maximum value for most of the cycle, right? So you can just redraw the same thing with a switching voltage source Vn between 0 and Vn. Okay, is that clear? Okay, so then what we are going to assume, of course Vn is much smaller than VLO. So you can assume that the circuit is, you can linearize the circuit. Okay, what is the time constant at this node? Let's call this x, right? Okay, so if you look at your current and voltages, right, at x, going to look like this. Vx is going to look like this. Okay. Then next we will plot the current through the capacitor Cp, which is ICP. And I have a pulse there. I'm going to have a negative pulse here, and so on. Okay. This equivalent circuit. Okay. So you understood the first two half cycles, right?
Sir, we are assuming that the noise is not large enough to change the switching.
Absolutely, that's right. That's right. Okay. We are already assuming that noise is much smaller compared to the VLO. Okay, and the switching instance. So what you are doing is, so you understood this first half cycle, it looks like this, second half cycle, it looks like this. So if you want to replace the whole thing by a single circuit, what is the difference between these two? The only difference between these two is Vn. Assume that the transistors are identical. Okay, the only difference is Vn. Vn has some time domain response. Okay, some noise in the time domain. Okay, except that, so what you're going to do is, you're going to redraw the same thing as here, except if you take during, so let's say this is the cycle, right? During this cycle, okay, you do have Vn here. During the second half cycle, you don't have any Vn. Okay, so which means this goes to 0. Okay, third cycle, again you have Vn because it's the left side of the circuit, and so on. Okay. Suppose you plot actually the output differential current. Okay, remember that the switching pair switches the current at the tail between plus and minus sides. So the differential side will go between plus ICP and minus ICP. So which means right? If you look at the current through Cp itself, ICP, the DC value is 0 because it's completely symmetric, right? But if you look at this guy, DC value is definitely not 0. So what does that mean? That means at the output, you actually, so obviously DC value is not 0 means you also have some low frequency component, which means flicker noise from that will get upconverted. Okay, that's what it means. That means that you will have some flicker noise at the output. Okay, flicker noise from the switches. This is the indirect path. The direct path we looked at last time, which is the input referred noise from the gate, at the gate, right? That does not get upconverted. But if you have some parasitic capacitance here, it gets upconverted through the current through the capacitance. Is that clear to everyone?
Only for the one cycle, like the positive cycle.
No. See, this is for all time, right? Yeah. See, okay. So what I mean is, obviously for most of the cycle the current is 0, right? But you do get current pulses at the 0 crossings, right? That means that, so finally if you look at this, if it has a non-zero DC, that means that the noise at very low frequencies does exist.
Sir, the pulses would come whenever ICP is possible.
No. When this is 0, this is also 0, right? Of course. So, okay.
Like ICP goes down when doing that at the negative.
That is this. That is this guy. You are able to see the negative pulse, right? You do get a negative pulse. So you get a positive pulse when it goes positive, when it switches one way. You get a negative pulse when it switches the other way, right? Okay, so let's see what the DC value is. What is ICP of T? You can write it as C dV by dt for the capacitor. Okay. Yes. So this is TLO. Output current noise.
But in action scenario, when you have a load, it will be filtered out.
When you have a load? Okay. No, because if you look at a receiver, you will not have a resonant load. You will only have an RC load. Okay. So then it won't be filtered out.
But flicker noise, does it have some contribution?
Flicker noise actually has some contribution because if it's an IF, it's not a problem. But if it is a direct conversion receiver, direct conversion mixer, you will have a problem. Okay. Okay. So this is the conversion gain for the noise for the indirect path. Okay. What do we see? Of course, the conversion gain increases with the frequency. Okay. So definitely, if you have a higher frequency LO, the noise through the indirect path will tend to be higher. Usually, it will be much lower than the other noise, but it's something to keep in mind. Okay, because it depends on the parasitic capacitance as well as your FLO. Okay. So let's say we can calculate SNR because we know the two conversion gains, right? Conversion gain for the signal was 2 over pi GM. Okay, of course you have okay. So obviously you want to minimize CP, you already know that. Okay. Okay. The other thing is, of course, if CP is similar to in value to, let's say if you assume it's similar to CGS of the transconductor, you can rewrite this in terms of FT and show that it's inversely proportional to FT. So you probably want to maximize the transconductor FT. Okay. I think that's it. So for noise, does anybody have any questions on noise? We are going to move on. Okay. Okay. So I'll assume everything was clear. Okay.
Why is it not indirect?
It's called indirect because, so if you remember last class, we saw what happens directly. So okay. So we saw what happens when you assume an input referred noise Vn at the gates of the transistors, and we saw what happens when it goes directly to the output through the switching action of the switch itself. But this one, what happens is, if you have a noise at the gate, if you have some parasitic capacitance, last time we didn't assume any parasitic capacitance. This is causing a current to flow through the parasitic capacitance, and that gets upconverted, right? So it is an indirect mechanism. Yes. Right now this is the SNR for the indirect switching noise. Of course the total SNR would be this thing. This is the SNR just for the indirect switching noise. Okay, because you want to take each noise source separately by itself, calculate the SNR and find out what you want to do to maximize it. Okay, so that overall you'll know what to do. Is there any assumption on the nature of gate noise? No, there wasn't. Right? We just assumed that it has some profile. So we found out what happens when it goes from input to the output. We saw what happens when it's low frequency, what happens when it's high frequency. Actually, the procedure we followed last class was the same as what we did in today's class. Very similar, at least. Okay? We didn't assume any profile. What we know is, if you have noise, so what we did was we found out what happens to the noise at the gate. Then what happens when it's low frequency, and we found that it moves away from the frequency of interest, right? And then when you go to when you look at high frequency noise, you actually get noise that's called noise folding. Okay, you get noise from higher harmonics. Okay, so we didn't assume anything special about the profile, and in fact, if you see, we didn't assume anything special about the transconductor, right? We just assumed some kind of GM. In reality, if it switches fast enough, it is fairly true. Only at the end we assume that the noise was 4kT gamma GM, right? Before that, so the basic analysis you can use it for any kind of transconductor based mixer, any kind of switch based mixer, switch and transconductor. Okay. So we'll look at a couple of more linearization techniques. So we covered some of them last class. So okay, so let's go through them one by one. We'll look at two of them in some detail, but predistortion, the idea is, so let's take the example of a current mirror. Okay, you have some input current and gets converted to a voltage. So and then eventually gets converted back to a current. Okay. If you look at the voltage here, what does it look like? The current to voltage obviously has a square root relationship, right? Okay. So this is, for example, the simplest example of predistortion. So effectively you're taking the input current which has some information, you're distorting it, okay, into a voltage with some kind of nonlinear relationship and eventually converting it back to a current. And when you convert back to a current, obviously, okay, going to look like this, okay, and if there is a mismatch, that will end up at the output, okay, causing an output error. That is well known. See, the other kind of predistortion which is very common is in bipolar transistors. This is kind of the classical . So remember that your differential pair has a tan hyperbolic function from input voltage to output current, right? So you can create an inverse tan hyperbolic at the gate, okay? If you do that, you'll get a very linear characteristic. Okay, for let's say input current to output current. Okay, so we know this is the tan H. Second thing, I think we looked at this before, piecewise approximation. Right? Remember the multi-tan H. So we took 3 differential pairs and separated them, right, with using the bias or the size. Okay. So if you have something like this, sorry. Something like this. Okay, we already looked at this, I think 2-3 classes ago. The other very common approach is feedback. Okay, we'll look at a couple of, we'll look at one example, which is called the MOSFET cross quad. Okay, so this is work done at Tektronix in the 70s. So let me draw out the circuit. Okay, you're going to cross couple M1 and M2 in this way. So let's say the input current is some signal current delta I. Okay, so what is our goal? We are going to try to synthesize a short circuit between A and B. Okay, that's what we are going to try to do. And this guy, this section actually gives some kind of positive feedback. Okay. Okay, so let's start analyzing this guy. So let's have 2 currents, right? So let's say bias plus minus delta I. Okay, I4 and 2 have I bias plus delta I. Okay, I1 and 3 have I bias minus delta I. Okay, so let's assume this current causes a delta VGS on each one of these transistors. Okay. Okay, and we are also going to assume that all 4 transistors are matched, of course. Okay. What is VAB? So VAB is, you have 2 VGSs here. Okay. For A you have V bias minus VGS4 minus VGS1, right? For VB you have V bias minus VGS3 minus VGS2. Okay, and we already know these guys. What we have done here is assume that delta, delta I causes some linear delta VGS change. So now we are calculating VAB. That's VA. That's VB. So you get VGS2 minus VGS4 minus, and we know both of these are equal, right? Okay, if the transistors are all matched. So what does this mean? Right? You tried putting a delta V, tried putting a delta I, your delta V was 0. So that means that the resistance should be 0. Okay? So let's say we go back to the same circuit and instead of this guy, okay, this delta I was actually a test source. Now we are going to put in the real V in and RS there. Okay, what is the output current? V in over RS, right? So which means it's extremely linear. Okay. Okay, so let's see. Okay. Oh, before that, actually, you also have an alternative version. Okay, if you find it inconvenient to apply your voltages here. Okay, so normally you want to apply your voltage at a high impedance path. Okay, so you have an alternative version of this which looks like this. Okay, you can apply your V in here at the gate of these two guys, and the same thing will appear here. Okay, this is another way to use the same circuit. Let us just look at the last guy. Just feed forward. So of course the drawbacks of feedback are, you have to worry about stability, you have to make sure the bandwidth of the signal, the bandwidth of the feedback loop, right, can only compensate for very slow errors, right, because it's usually much smaller. Okay, this thing is called the cas comp. Don't ask me how they thought of these names. Okay, so it's probably something to do with Cascode and computer or something, right? Computing, but it's called CASCOMP. Okay, so it looks like this. Okay, looks something like this. One, two, and apply Vn by 2 and minus Vn by 2 here. So your M5, M6 is your error amplifier. What it's going to do is it's going to calculate the error between C and D and amplify it and add it to the output as a current. Okay, so let's call these. That's your differential current I. This is your error current. I5 and I6. Okay, so the next thing to do is you're going to calculate VR, okay, which is VAB in terms of Vn by 2 minus VGS1, okay, and VB is minus Vn by 2 minus VGS2. So it's Vn minus of VGS1 minus VGS2. Okay. So the signal is going to cause a delta VGS between 1 and 2. Okay. And you can write it in terms of your I bias, W over L and everything, and the approximation you're going to make is, so okay, 2 so you'll get something like this. Okay. This first term is your VGS minus VT times, and you're going to make 1 plus x whole power n, right? You can expand that. So you'll get 1 plus delta I over 2 I bias from this, minus of 1 minus delta I over 2 I bias. So this is your linear approximation. So your current, differential current is just VR over R, which is, this is your ideal term which you want, minus this is your error term. Okay. What else do we know? Oops, sorry, it's next guy. We also know the voltage gain from, let's say, the positive input to C, okay, is approximately -1, right? And same thing on this side. So you know the voltages at C and D approximately. So let's write that also. So this is Vc and Vd. Okay. Then you can write I6 and I. Okay, so you know I5 and I6. Now you can write expressions for I5, the I1 total and I2 total, the two differential currents. Minus. Because the gain of these two guys, so input to C, right? So the gain from input to C is approximately -1, because the input impedance is approximately 1 over GM of this guy, right? Yeah. I'm assuming, in fact, all sizes are matched right now, right? Almost. Well, these two sizes definitely 1, 2, 3, 4 are all matched. Okay. And 5 and 6, you're going to see, you're going to size them based on how you want your error. So that's what I'm getting to here. This was your error, and this is your feed forward what you have added. So you're going to try to make this whole thing to be cancel out. So you ideally want only Vn over R at I1. Similarly, you have I over I minus delta I on the other side, and again that will depend on GM5 or GM6. Okay. So you set this too. So you're going to design this guy. Okay. So this is another way. This is the feed forward method. One example. Okay. So we'll stop here, and we'll continue next class. I think we are almost coming to the end.